In this video, we'll be talking about the divergence test. Now, it's important to understand that the goal of most of these sections is to evaluate whether or not a series will converge or diverge. So the divergence test specifically tests whether or not a series could be divergent. It also behaves very much like that of a U-sub in integration. When using integration skills, your first step is to attempt to integrate with things that you know, algebraic manipulation, and worst case scenario, U-sub. After that, you start using other methods based on what you see. Well, the div test is very much like that U-sub. You should probably attempt to use this almost in every case, first and foremost. So the divergence test is specifically this. If we have a series A sub k converges, if I know that this series converges, then I know that the limit as k goes to infinity of the sequence of terms is equal to 0. Let's make sure that that makes sense. First off, if I know that a series converges, it means that I know that the series will add up a number of terms up until they get to a certain, an infinite number of terms, and that should all equal to a very specific number. This should coincide with the logic that if the limit as k goes to infinity of a sub k is equal to 0, well, if this thing converges, then those terms, each individual term as I add them up, has to get smaller and smaller, getting closer and closer to 0. Okay, so this is the divergence test in terms of its theorem. The actual divergence test is that this implies the logic contrapositive of this, which is if the limit as k goes to infinity of a sub k does not equal to 0, so again the contrapositive takes and swaps the order of these two things and negates their statements. So if the limit doesn't equal to 0, then I can conclude the series a sub k diverges. So this is the actual rule that we'll be using, is that if the limit as a sub k equals to 0 on the sequence, then the series itself is divergent. Sorry, does not equal to 0, then it is divergent. So this does not prove in any way that any series is going to be convergent. It will only ever state that those series are divergent. Now there is a proof for this, and the proof that we use to prove this is, again, the main basic step of how to evaluate series or whether or not a series is convergent or divergent. And that's using your partial sum sequences. So if we assume that we have the summation of a sub k converges. Okay, so this is our proof of this. If we start off with, well, this thing converges. So I'm starting with this statement right here. Okay, this is not something I can prove. This is proved by the contrapositive logical rules. I'm going to go ahead and start with this and come to the conclusion that this is then also true. So if this thing converges, then I'm going to let the s sub k be the kth partial sum of the series a sub k. What I'm trying to say then is that s sub k is the nth, so s sub k is really equal to the sum of k equals 1 to k of a sub k. It's technically taking up all the values, plugging in 1, 2, 3, up until I get to k, and that's the sum of all those values. Now, if this series here is convergent, then I should be able to state that the s sub infinity, which is the same concept as the limit as k goes to infinity of s sub k, is then also equal to the limit as k goes to infinity of one less term. Okay, so the idea is here is I'm taking the limit of the kth partial sum, but I'm also taking the limit of the kth minus 1 partial sum, which means that I'm looking at these two partial sum series, and this is the kth number of terms, and this is one less than that. So if I do that, that means that s sub k minus s sub k minus 1 is really actually equal to, well, it's a sub k, because this is the list of terms a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub k, and this one's all the terms all the way up to a sub k minus 1, which means that there's one extra term in here that this one doesn't have. So if I subtract those two values, I get this. I also know that if I take the limit of this side here overall, the limit as k goes to infinity of s sub k minus s sub k minus 1, well, these two separately both go to the same value, s sub infinity. There's some number. which means that if this goes to S sub infinity and this goes to S sub infinity, that means that when I subtract the two, I get 0. So the limit of this side has to be equal to 0, therefore the limit of a sub k also has to be equal to 0. So the implication is that if this series converges, then by definition, the limit of the sequence must then equal to 0. And again, that's the proof of the divergence test in such a way that I will end up using its contrapositive. I will use its contrapositive to actually prove whether or not a series is divergent. Again, I will never use the div test, which is what I'm going to call it, the divergence test, the div test, to determine whether or not a series is convergent. I can't do that. That's not what the series, or not what this test can do.